So in my last lecture, I discussed the advanced bipolar processes. Now we will concentrate on MOS process. And you know, in the present VLSI, major market area or major percentage of consumer electronics or application wise, the MOS has captured the major marketplace. So about 65 to 70% VLSI chips are fabricated using CMOS or NMOS. So the MOS process technology and its advancements are very important to know, and I will discuss one by one the developments of first NMOS process, and then I will discuss CMOS process. Before going to MOS process, I spent small time on the basic MOS structure and its device parameters. So first slide, you can see here is basic MOS structure, and here you can see it is having 4 terminals. One is the source, another is the drain, third one is the gate, and fourth one is the substrate. In case of NMOS device, source and drain are highly doped N region, and substrate is p-type, and gate is silicon dioxide. Thin layer of good quality silicon dioxide is used as a gate material, and top of the silicon dioxide metal film is deposited for taking contact. So normally source and substrate are grounded in normal applications, and drain in case of NMOS, the drain is made positive and gate voltage is applied, and for different gate voltage the operation of the MOS transistor is different. So the basic operation is like this: if we apply voltage at the gate with respect to ground, if you apply a positive voltage, then what happens? Here negative charges will be induced, the channel will be induced, negative charge will be induced, to which we will connect the source and drain. A current will flow from drain, source to carriers will move from source to drain. So as a result of which you will get a drain current. That is the basic function of a MOS transistor. Until unless you apply a voltage at the gate, and until unless a channel is formed, the transistor is not conducting, isn't it? And one important parameter in case of MOSFET is the threshold voltage, and the threshold voltage is normally defined to be the gate voltage at which the surface of the semiconductor is at the onset of strong inversion. This is definition of the threshold voltage. Means you are applying here voltage. In case of NMOS transistor, you apply a positive voltage. So here it is below the gate, it is a P substrate, dopants are P. When it is inverted, means here the electrons are accumulated, so the channel will be formed, and that is known as inversion. So then a direct conduction path from source to drain is available, and that conduction path is controlled by the gate voltage. Okay. So this threshold voltage is one important parameter in our MOS technology. We have to see how a stable threshold voltage is achieved in a MOS transistor. If threshold voltage changes with time or from device to device, so then the circuit will malfunction and will not get a good quality circuit, and its performance also will be hampered. Now, the threshold voltage for NMOS is given by this relation Vt. Vt is equal to twice phi f plus Ks T ox divided by K ox into under root 4 Q Na phi f by Ks epsilon naught, where phi f is the Fermi level, which is given by Kt by Q ln Na by Ni, where K is the Boltzmann constant, T is the temperature, Q electronic charge, Na is the acceptor concentration, that is T region, which is substrate, Na is the substrate concentration, that is channel before inversion, that is P substrate in case of NMOS, and Ni is the intrinsic concentration of silicon. So that is the phi f Fermi level. And Ks and K ox is a relative dielectric constant of silicon and silicon dioxide. T ox is the gate oxide thickness, this is the T ox. Na and Ni acceptor concentration and intrinsic carrier concentration. And epsilon naught is free space permittivity. Now, threshold voltage shift due to semiconductor metal work function and presence of oxide charge and interface charges is like this. Threshold voltage, although the relation is given by this equation, but it shifted due to the presence of the oxide charges. That's why I mentioned earlier also, in case of MOSFET, the oxide should be free of trapped charges or interface charges. And due to the change of metal work function, this is phi ms. Due to the presence of metal work function phi ms, the threshold voltage also changes, and that change is given by this relation. Delta Vt is the threshold voltage change, is given by phi ms minus Qf plus Qit plus Qmi, gamma mi, and Cox. And Qit is the trapped charges, Qf is the fixed oxide charge, and gamma mi is a constant, and Cox is the gate oxide capacitance. This Cox is the gate oxide capacitance. Okay, these are all charges trapped inside the silicon dioxide. Because of that, the threshold voltage will be shifted. Okay, so this particular term will be added with the Vt. This is a change. Over and above this relation, this delta Vt will also come into the picture. Now, we know there are three regions in MOSFET operation, and those regions are known as sub-threshold region, which is defined by VGS, gate source voltage is less than Vt. This is shown in this diagram. This is the source N plus, this is a drain N plus, source is grounded, this is a channel region, this is a gate oxide, and this is a metal. So when the gate voltage, gate to source voltage is less than the threshold voltage, Vt is the threshold voltage, then this is known as sub-threshold region. Next region is known as a linear region. This is the second picture. Linear region is VGS is greater than Vt. That means gate to source voltage is more than Vt. So an inversion layer has already been formed here. This is the inversion layer, channel has been formed. And there the drain source voltage is greater than 0 volt. If you apply drain source voltage is greater than 0 volt, but it is less than VGS minus Vt, then you will get the linear region. So linear region is defined by this condition. VGS is greater than Vt, and VDS is greater than 0 but less than VGS minus VT. So the second picture here is the linear region. Third one is the pinch off region. Pinch off region, in this particular region, the conditions of biases are like this. VGS is greater than VT. So that means the gate voltage has to be more than threshold voltage. Otherwise, channel will not be there at all. So channel is formed. Now you are changing the drain voltage. So if you change drain voltage, here drain voltage is less than VGS minus VT. But in the pinch off region, when drain voltage is greater than VGS minus VT, so then what happens? So here this is reverse bias, substrate to the drain is reverse biased because it is positive. The N plus is positive, so it is reverse biased. So because of reverse bias, depletion layer width will fall. So this depletion layer width pushes the channel into towards the source region. So as a result of which, just near the drain region, there is a depletion of the carriers, and here pinch off will occur. So this pinch off region is defined by this. So all the three regions, different models are used to calculate the drain current. In threshold region is not so simple, is a little bit complicated, but linear region and pinch off region is very easy, and you can get the drain current expressions as follows, is shown here. In the linear region, the drain current is given by W by L, B effective Cox, VGS minus VT into VDS minus VDS square by 2, where W by L is the channel width to length ratio. Channel width and length ratio. You know what is the channel length? Channel length is the gap between source and drain below gate. This is the channel length. And channel width also, you know, the over the gate region, the length of the oxide, that is the channel width. Okay. So now if you go into the first diagram, I can show you. That is the first diagram is 3D diagram. Sorry. Here, this is the channel length. From here to here is the channel length, and channel width from this region to this region. This is the channel width. Okay. So W by L ratio is one governing factor in MOS currents and many MOS parameters. Okay. So W by L ratio, the channel length versus channel width, is very important in determining the current, IDS drain current. Now, this is the linear region. Linear region is defined by this, we know, and there the current is given by this. VDS is a drain to source voltage, and VGS is gate to source voltage, and VT is the threshold voltage. Now the pinch off region. In a pinch off region, the drain to source current is given by W by L, mu effective, this is effective permeability. Cox is the oxide capacitance, and VGS minus VT square by 2. This is the current drain current expressions in the pinch off region. And pinch off region is defined by this: VGS is greater than VT and VDS is greater than VGS minus VT. And in a sub-threshold region, the drain current is proportional to exponential KBS Q VGS by KT, where the VGS is less than VT, because in a sub-threshold region is important in particular in short channel devices, and their modeling is not as simple as linear region and the pinch off region. So in the sub-threshold region is a proportional to K substrate Q VGS by KT, where K substrate is a constant and it depends on gate oxide thickness and substrate doping. K substrate, the substrate concentration, this is a function of gate oxide thickness and substrate doping. Others are known. K is a Boltzmann constant, T is the temperature, and VGS is the gate source voltage, and others are known. So this is a sub-threshold region. So with this background, we will just now start discussion on how a MOS is fabricated. So MOS technology, process technology, has got certain features which we have to remember before fixing up certain process suitable for fabrication of NMOS or CMOS. Formation and protection of gate oxide is the most critical in MOS process. Source and drain is not so critical, because highly doped source and drain region you can form anyway. But gate is very critical, because if you want to reduce the device size, channel length will reduce, and at the same time gate oxide thickness is going to reduce day by day, because you want to work as a low threshold voltage. So gate oxide has to be thin, and the threshold voltage is one of the controlling parameter of the threshold voltage is the thickness of the gate oxide, quality of the gate oxide, as well as the channel doping region. Okay. So next is the reduction of the threshold voltage can be accomplished by employing polysilicon as gate material to replace the metal gate, and the process is known as silicon gate technology, because metal is replaced by silicon, means polycrystal silicon. Why? Because we need a stable threshold voltage, and stable threshold voltage is achieved by silicon gate, because the polysilicon and the oxide together has got certain barrier height. If you use metal and oxide, that barrier height may degrade with time. Because of the polysilicon, you will have the barrier height fixed, and it will be stable, and you will get stable threshold voltage. That's why polysilicon gate is replacing the metal gate. Metal means directly on oxide you are using metal, but we will use oxide, then polysilicon, then metal. Silicon dioxide will be there. Okay. Now, self alignment between the gate electrode and the source and drain regions can be obtained by ion implantation with gate as the mask. Here you are getting automatic alignment, because gate oxide can act as a mask for implantation source and drain regions. So that's why after field oxidation is over, then you go for photomasking of the gate is created, and after that source and drains are implanted. There's automatic alignment, you will get it. Self alignment. Self aligned process enables fabrication of short channel MOS that exhibit good high frequency response. Short channel and long channel MOS, there are two categories. Only difference is channel length is small in case of short channel, and I will show you later on the table where how much channel length is used at present and how much was used few years back. Short channel devices obviously has got certain problems, and we have to overcome those problems, and we will do it by certain techniques, by incorporating certain techniques in process technology. Now, as the transistor size goes down, gate oxide thickness also goes down, operating voltage are also reduced, both diffusion and drift currents must be taken into account. We know MOS device operate in the drift current mode, majority carrier device, but if you scale down the device, size of the transistor is reduced, operating voltage reduced, as well as gate oxide thickness is nearly nowadays using 40 to 50 angstrom unit. So there not only diffusion, drift currents, not only drift current but also diffusion current will play a major role in deciding the drain current. So we have to consider both diffusion and drift currents in very short channel devices. So these are the salient features of MOS process technology. Now we discuss silicon gate NMOS fabrication process, and we confine our discussion in NMOS, not PMOS, because NMOS is popular than PMOS because of higher mobility of the electrons compared to the holes. So in this case, in the diagram, you see initially here is the first you take the substrate. This is a P substrate is taken, and then you grow oxide, 1 micron thick oxide, second step. This is a masking oxide, initial masking oxide. Then you go for photoresist process, that is photomasking, and using the photomasking you are creating the active area. You are just finding the active area, then field. This is the field oxide. So in this diagram, then fourth diagram is this one. So this region here you are creating, and this is the active region, and this is the field region. So field region is protected, and active region windows are open. Windows are open in the active region. Okay. So here source, drain, gate, everything will be fabricated in this active region, and then you deposit polysilicon before growth of silicon dioxide. Thin silicon dioxide is grown here, and that oxide is about 800 angstrom to 1000. This is a earlier version of MOS. Nowadays that gate oxide thickness has gone down to even less than 1000 angstrom. So I am talking about the first stage of the MOS process. So their gate oxide thickness were in the range of that values, and obviously that is grown using the dry oxidation process, where the fixed oxide charges will be less, interface oxide trap charges will be less. So after the gate oxide is not patterning, gate oxide is formed. Here you see gate oxide is formed, and after that polysilicon is deposited. 1 to 3 micron thickness polysilicon is deposited, and that polysilicon is patterned. Here gate is patterned. So polysilicon is removed, but the oxide is there, and now through oxide you can now implant source and drain, because here oxide thickness is very less, and it will protect the silicon for creating surface damage. High energy implantation is being done through thin oxide. The implant species can penetrate, and damages will be less at the interface, so that leakage current will be low. So that's why when you are doing high energy, high dose implantation, then it is done through thin oxide layer, not bare silicon. Next is N diffusion, 1 micron deep. Source drain is formed here. Okay. After forming source drain, then you again deposit oxide, and contact patterns are formed by photomasking techniques. Contact holes are cut here in the gate, here in the drain, and here is the source. Okay. Source, gate, drain contacts are defined here, and then metallization follows, and you will get the gate electrode here, source is here, and drain is here. And substrate, you can take one contact from the top, so that you can get both, and substrate and source are connected together, and it is grounded normally. Gate terminal you apply certain voltage, and drain you collect the carriers. You will get drain current. So this is the simplest possible process sequence of fabricating NMOS transistor. Very simple process, which were followed at the beginning. Is a large channel device, not a short channel device. Okay. Now, next step is a Salicide NMOS process sequence. Salicide means self-aligned silicide. Earlier was silicon gate. Now we'll use the Salicide gate NMOS process, and that is automatic alignment is there in Salicide technology. That's why it is known as Salicide. Self-aligned silicide is known as Salicide. So Salicide NMOS process sequence now we'll discuss. So there, after low-cost formation, this is field oxidation low-cost formation. Thin gate oxide is formed. This is the thin gate oxide you see here. Thin gate oxide is formed. Polysilicon is deposited and patterned. Here is the polysilicon is deposited and patterned. Source drain implanted. Okay, then source drain N plus and here N plus are implanted. So after low cost process, thin gate oxide, this is the thin gate oxide of the order of 1000 angstrom or even less, is formed by thermal oxidation. Then deposit polysilicon and pattern polysilicon in the gate region. Source drain are implanted here and here. So this is formed. Next, formation of side wall oxide spacer. In earlier cases you have seen, we again open a window, oxide is deposited here, and open a window on gate, and there you deposit metal. So there you are wasting some of the gate area. So in self-aligned process or high density MOS process, so that areas has to be saved, so that you can increase the density of the components by reducing the size of the MOS transistor. So that you can do by the creation of sidewall spacer. What is sidewall spacer? At the sidewall of the gate, you have to create an oxide plug, that is sidewall oxide spacer, which allows some space so that the gate is separated from the source and drain. And how it is fabricated is shown here in this diagram. The spacers is formed by depositing oxide layer about 200 nanometer thick and etching it with anisotropic RIE. All the oxide in the field will be cleared except at regions next to sharp steps where deposited oxide is thickest. This is the oxide spacer here and here. Below, what is this? This is the gate oxide. So now what is done? A thick 200 nanometer oxide is deposited over the entire wafer like this. Now when it is deposited at lateral, here also oxide will be deposited. Now what you are doing, you are just using RIE technique, you are etching back the oxide. If you etch back, so from here it will etch back, here it will etch back, and same thickness will be here, here it will etch back. And as the thickness at the sidewall space is more than the thickness here and here, so it will remain. Okay, so that means this polysilicon is totally covered from three sides by oxide. Bottom is gate oxide, and this two side is spacer, and that spacer is again oxide spacer. Okay, so this oxide spacer is formed. Next step, what will you do? Next is the metal is deposited, either titanium and cobalt. You see, this is the spacer. This is the spacer. Now on the top, this earlier the complete thing was silicon. Here the complete thing was polysilicon. On top of that, the metal film is deposited, and that is either titanium or cobalt film is deposited, and then it is annealed using rapid thermal annealing. You know how to fabricate salicide. Salicide fabrication sequence is already explained in metallization lecture. So you have to deposit silicon, you have to deposit silicon or polysilicon on, and then you deposit the metal whose salicide you want to form, and here we have chosen titanium or cobalt. Then you go for rapid thermal. So wherever silicon and metals are there, they will react each other, solid phase reaction, it will form silicide, and wherever the metal is deposited on oxide, no silicide will form. Okay, so that means here silicon dioxide and here silicon dioxide, no silicide will form. Here this is the N plus source and N plus drain, this is silicon, and this metal titanium or cobalt react with silicon, and silicide has already formed. You see, this is silicide contact, this is also silicide contact, and on the gate region polysilicon was there, and polysilicon and the top metal will react, and it will also form silicide. So silicide has formed on the top of polysilicon here, silicide has formed in the gate contact source contact region, and silicide has already been formed also in drain contact region. Okay, so unreacted metals on the oxide are removed selectively. That is in silicide process. Next, it is found that titanium thickness should to be 1/5 of the original junction depth in order to avoid excessive leakage current. The thickness of the titanium should be small, otherwise total silicide thickness will be large, and then since the emitter junction, not emitter here, sorry, the drain and source junctions are shallow, then the silicide may reach close to the source drain junction. What is the junction? Source and drain with substrate, and those junctions are reverse biased. So now if silicide thickness is large, so this interface may reach to the junction and leakage current will increase. That's why the titanium thickness should be very small, so that it will consume a small amount of silicon and smaller thickness silicide is formed. That is to avoid excessive leakage current. Now, this is the final structure after glass passivation, reflow, contact opening and metallization. Glass passivation layer is deposited, contacts are formed and metallization follows. Because once silicide is formed, actually active electrodes of the gates are already formed. Next process are the passivation and contact lead formation. So that is done by metallization process. The use of Salicide process can significantly reduce the parasitic series resistance of the MOSFET. It can significantly reduce parasitic series resistance of the MOSFET. Okay. Although titanium silicide is highly popular in Salicide process, metal silicide, MOSI2, that is metal silicide, MOSI2 may be a better choice for NMOS application because of its lower barrier height of the order of 0.55 electron volt, which provides a lower specific contact resistance. Specific contact resistance of molybdenum silicide is low compared to titanium silicide. But the problem is molybdenum silicide formation temperature is higher than titanium silicide. Okay. So because of the lower formation temperature, nowadays people are also using cobalt silicide. That is also another attractive choice for silicide contact formation in source and drain junction. So here, what is the gate? Gate is the first layer is oxide, then you polysilicon, then you are getting silicide. Okay. The combination of oxide, polysilicon, silicide together forms the gate region. And contact of source region are not metal contact here, silicide contact. Since silicide formation is automatic, so self alignment process is used here, and automatically you can allow the device size, you can get device size smaller than earlier process. Okay, this is salicided NMOS process. Now I am coming to more advanced device features, that is short channel devices. In a short channel devices, effects predominates which is known as hot carrier effects in short channel. Short channel means the channel length is extremely low, sometimes it enters in the submicron region also, less than 1 micron. So there hot carrier effects is predominant. So we have to know what do you mean by hot carriers. Then we will see its effects, then we will see how it can be removed and what are the modified processes available to remove the hot carrier effects. So in the reverse bias drain to substrate junction, the electric field may be quite high in the short channel devices. Field is the DVDX. Gate voltage, gate to substrate voltage is reverse biased, and at the junction, drain to substrate is reverse biased, drain to substrate is reverse biased, and drain to substrate junction, a field will be created because there a depletion layer will be there, reverse bias, electric field will be created, and that electric field is in modern short channel devices of the order of 10 to the power 5 volt per centimeter. It's very high field because your junctions are shallow, isn't it? And the field is volt per centimeter, and it is submicron region. Shallow junctions is of the order of nanometer region junctions, and now their automatically field will be extremely high. So because of this high field, carriers which are injected into the depletion layer are accelerated by the high field. Carriers that are injected into the depletion layer are accelerated by the high field, and some of them may gain enough energy to cause impact ionization. Because of the high field, those carriers will energize and they will move with higher mobility, and they cause impact ionization. These carriers have higher energy than the thermal energy, and they are called hot carriers. That is the reason they are called hot carriers, because their mobility is so high, they are so energized, so that it is more than the thermal energy. What is thermal energy? KT. KT is the Boltzmann constant, and T is the temperature, and KT energy is the thermal energy. And the energy acquired by the carriers in that high field is more than KT. That's why it is known as hot electron. And now the holes may terminate to the substrate, giving I substrate, because of the impact ionization. What happens? Both electrons and holes will be created, and they will again hit with other silicon atom, and then electron hole will be created in the reverse bias region, and the holes may terminate to the substrate, giving to substrate current, and holes also may find their way to source, lowering the source barrier to induce electron injection. You see, there may be some electron injection in the source because of these carriers. Drain channel source structure now acts as NPN transistor with floating base and collector under avalanche multiplication. Collector is the substrate, drain junction will act as a collector, source will act as emitter because it injects carrier some sort of, and P is the substrate region is the channel, so NPN region, so it works similar to an NPN transistor. So you may end up with a parasitic NPN transistor in the short channel devices because of the movements of the hot carriers. Okay. The electrons may be attracted to the positive gate and may tunnel into the oxide to produce gate current. Trapped electrons in gate oxide may change VT, which is the threshold voltage of the MOSFET. So what happens, you see, this is another severe effect in the short channel devices. Because of the hot carriers are energetic, so those carriers may be attracted with a positive gate, the electrons. Hot carriers are both electrons and holes, and electrons having higher mobility, they are light, and they will moving with higher velocity, higher mobility, and those electrons may be attracted in the positive gate, and some of the electrons may cross the barrier of the oxide, and they may be trapped inside the oxide. So if the electrons are trapped inside the oxide, they will end up with some charge, and that charge will reduce the threshold voltage of the MOSFET VT. So that means in short channel devices, because of the hot carrier effects, the function below the gate oxide is similar to a transistor also, and there are also possibilities of the bad quality of oxide and threshold voltage shift. Okay, because because hot carriers will be trapped inside the oxide. So this is the generation of hot carriers and its consequences in device performance. Now, how to remove those problems? Those problems are removed by drain engineering. There is a topic in MOSFET which is known as drain engineering, and here one solution is a lightly doped drain structure, which is known as LDD structure. What is done in LDD structure? Hot carrier effects are alleviated by LDD structure, which reduces the drain field. Actually, high electric field is developed at the drain substrate reverse bias junction, and we have to reduce that electric field, and that can be reduced by addition of another drain region which is lightly doped. In LDD structure, the drain is formed by two implants. One of these is self-aligned to the gate electrode, and the other is self-aligned to the oxide spacer at the edge of the gate. Oxide spacer I discussed in last slide. So there are two drains are formed in LDD structure. One is automatically aligned to the gate electrode, and other is self-aligned to an oxide spacer at the edge of the gate. Lateral dimension of the oxide spacer is nearly 75% of oxide thickness. So what is that oxide thickness? Gate oxide thickness is 75% of the oxide thickness. In a typical NMOS, the lighter drain is used by P-type, that will be lighter drain is N-type phosphorus diffusion. P is the dopant. Like I am discussing NMOS, so lighter drain is phosphorus doped, 10 to the minus 3 centimeters square is the dose, and higher doped region is arsenic, 10 to the minus 15 centimeter minus 2 is the dose. And LS is the length of the spacer is done 160 nanometer, which is 0.16 micron. 0.16 micron is typically the spacer length. Electric field is reduced to an acceptable level near the gate edge because of this lighter drain. If the drain region is highly doped, then electric field was achieved very high, but drain is separated into two regions. One is lightly doped, another is highly doped. And in the lightly doped is very near to gate oxide, so automatically there the field will be lower, and the hot carrier effects will be minimized. So that is the technique which is known as lightly doped drain structure, LDD structure. I will discuss in detail on LDD process. Another drain engineering in NMOS is a large angle tilt implanted drain process, which is known as lattice process. One is LDD MOSFET, another is lattice MOSFET. Lattice is large angle tilt implanted drain process. And what are the features of this lattice process? They are mentioned here. In submicron regime, LDD structure loses its limit because you are creating two drain. One is lightly doped and another is highly doped. And if you use two drain, so automatically you cannot reduce the drain region extremely small. So you are increasing the drain region. So their high density theme is lost. We need drains should be as minimum as possible drain area. But if you use two drain, automatically one is lightly, another is largely doped. So then you are increasing the drain region. So that is its limitation. In a short channel, in submicron regime, as the the channel length is reduced, as well as source and drain junction are shallow, as well as the source and drain regions are also narrower. So that can be achieved by lattice process. Better results can be obtained by implanting phosphorus for a dose of 1 to 8 into 10 to the power 13 per centimeter square with a tilt angle 20 to 60 degree. That is a tilt angle implantation from the source and drain side, and by rotating the wafer stepwise. Now, tilt angle rotation will penetrate the dopants below the gate region, not with that concentration, and their drain size can be reduced. Okay. An example is given here. In minus, that is a lightly doped grain, its dose is 10 to the 13 per centimeter square. LS here is 0.08 micron. That is a LS is special length for an optimized 0.25 micron device structure. For 0.25 micron device structure means the total length of the device, channel, source and drain is 0.25 micron. There the oxide spacer length is 0.08 micron, and there the lightly doped region will be below that, that is also 0.08 micron. Devices with better reliability can be obtained by lattice using scheme of off-axis implant, which offers better gate control action over the LDD region. Lattice offers better gate control action over the LDD region. So these are the two methods, drain engineering methods, by which the short channel effects can be improved. One is LDD structure, another is lattice structure. Okay. So in the next class, I will discuss the LDD structure of MOSFET, how the LDD structure is formed, and the details of the process sequence of the LDD MOSFET in MOSFET. Okay, let me stop here. of increase of